Okay, so like I said, this chapter deals with more some different properties of the single triangle. It's a very great chapter. We're only going to cover 4 sections. We will cover 4 this week, and in review, it will have our tests in here on this chapter by next Wednesday. And that leaves us 4 days before Thanksgiving. 2 of those we're going to do these geometric turkeys. That'll be on Monday and Tuesday. And then next Thursday and Friday, we'll probably start chapter 6. Cover 1 section in that, and then we'll have another day where we do some instructions or something. I haven't quite decided for sure. But that'll lead us up to Thanksgiving, and we'll get through chapter 6 and test on that before we go for Christmas. Okay? So, today we're talking about the bisectors of triangles, and the first one is called the perpendicular bisector. And you know what the word perpendicular means, and you know what the word bisector means. And so we're going to put the two together. Okay? A perpendicular bisector is a line, a segment, or a ray that intersects a segment at its midpoint and is perpendicular to the segment. Okay? So it's perpendicular and it bisects. Now this first example is just a bisector. Okay? This says PQ bisects AB. What happens when you bisect something? What do? Makes it into 2 equal parts, and in a segment it goes through the midpoint, right? Okay, so that's just being a bisector. PQ is a bisector of AB. But if we come over here, RS is a perpendicular bisector. So it still goes through the midpoint, making it 2 equal parts, or 2 degree apart. But it also is perpendicular to it, which means it creates a right angle. Okay, so it does 2 things, it's got 2 purposes. Alright, so we have what's called the perpendicular bisector theorem. And it says, if a point is on a perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So this line CD is the perpendicular bisector of AB, which means it goes through the midpoint and it creates a right angle. Okay? It also tells us that any point that lies on that line is equidistant from the endpoints of the segment. So this point C right here is equidistant from the endpoints. Okay? It's equal to both of those endpoints. Any point that lies on that line, I have to create another one. We'll call this right here point E. This point is also going to be equidistant from the endpoints of the segment. We have the converse of the segment also. And the converse basically states the opposite. It says, if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So, we have this point E, and it is equidistant from the 2 endpoints of that segment. Okay? This is A and ED are the same. And this theorem says that it lies on the perpendicular bisector. Okay? So, it's perpendicular to the segment and it bisects the segment. So that's the converse of the perpendicular bisector theorem. Okay, so let's do a couple of examples. It wants us to find the length of AB. What's the length of AB? 4.1. How do we know that? Okay, A is equidistant to both of those, but how do we know that? A lies on the perpendicular bisector, doesn't it? And if A lies on the perpendicular bisector, it is equidistant to both of those endpoints. Okay? And we got that from the perpendicular bisector theorem. Okay, now let's look at this next one. I'm going to answer the first part. We're going to go back. The second part, we'll go back to the first part. In this one, X is equidistant from W and from Z. Okay? So what does that tell me about X? What does it lie on? Brendan. It lies on the perpendicular bisector. So what does that tell me about angle WYX? It's a right angle, right? Okay? So WYX is 90 degrees. Now I didn't give you a value really to be able to figure out WY, but what is WY's relationship to something in the picture? Okay, it's congruent to YZ. Okay, so these two are congruent to each other. So let's say I said that YZ was 3. What is WY going to be? All let's look at this next one, RT. RT, does that segment have a relationship to anything? To what? To QR, okay, or RQ, okay, they're equal, right? Okay, and so I need to find X, and then once I find X, I can go back and find RT. R lines with the perpendicular bisector, so those two segments are equal to each other. So I'm going to set 2x plus 3 equal to 4x minus 7 to solve. Subtract 2x from both sides, add 7 to both sides, and so x ends up being 5. But it's asking me to find the length of RT, so then I got to go back and find that length. RT is 4x minus 7, so that's 4 times 5 minus 7. That's 20 minus 7. So that tells me that RT is what? 13. Good. Okay, so that's what happens when you have points that lie on the perpendicular bisector of the segment. Now the next thing we want to talk about is how this relates to a triangle. But before we do that, we want to talk about what concurrent lines are. Concurrent lines is when you have 3 or more lines that intersect at a common point. See how I've got lines A, B, and C, and they all intersect at that point right there. That point is called the point of concurrency. Okay? Where the 3 lines intersect, that point is called the point of concurrency. Okay? Now, if you take a triangle and you draw all 3 perpendicular bisectors, okay, they are going to intersect at a point called the circumcenter. So look at this triangle right here, this acute triangle. If I draw each perpendicular bisector, so like this right here is the perpendicular bisector, this is a perpendicular bisector, and this is a perpendicular bisector. Okay? If I draw all 3 of them in a triangle, those 3 lines are going to intersect. And they're going to intersect at a point called the circumcenter. Now, the prefix circum, it means around or encircling. And you're going to see why that's important in just a minute. Around or encircling. Now let's look at the obtuse. If I draw the perpendicular bisector here, I've got a perpendicular bisector here, I've got one here, I've got another one here. Okay? If I draw all 3 perpendicular bisectors, this time they intersect outside the circle, but that point of intersection, that point of concurrency, is still called the circumcenter. If you did it on a right triangle, okay, a right triangle, they're going to intersect on the actual triangle itself, and that's called the circumcenter. And that point is created by the perpendicular bisectors. Now, that point also has another relationship, okay, and that we get from the circumcenter theorem. And it says that the perpendicular bisectors of a triangle intersect at a point called the circumcenter that is equidistant from the vertices of the triangle. So, you look at this picture down here at the bottom, each one of these black rays are perpendicular bisectors. Notice that they all intersect at this point. That point is called the circumcenter. We learned that up above. That point also has another relationship in the triangle, and it is that it is equidistant from each of the vertices of the triangle. Okay, so it's equidistant from each of the vertices of the triangle. Okay? Now, I think in the past, I can't remember, but I'm pretty sure that we've covered what it means to circumscribe a circle about a figure. If not, I'll tell you what it means. If you circumscribe a circle about a picture, or about a triangle, that means that you draw it so that each of the vertices lies on the triangle. Now, that's not a very good picture, okay? But that's called circumscribing a circle about a triangle. It's also called describing a triangle, okay? But remember how I said circum meant around or encircling, okay? If I did that, if each one of the vertices lied on the circle, this point right here, that point right there, acts as what for the circle? It's the center, right? Because each one of these acts as a radius, right? All the radii of the circle. Okay. Also, we talk about circumference, right? You know what circumference is? What's circumference? It's the distance around. It's around or encircling a circle. It's the distance around. Okay. So that word means quite a few things. Okay. So why is this important? How would we ever use this? Okay. That's always the question. Okay. Because it's wiring your brain differently, like my man said in the video that I showed you. Let's say you are an architect. Okay. And you are going to build a building. Okay. Your building has 3 exits, okay? One right here, let's say there's one right here, and we'll put one right there, okay? I want to put the bathroom equidistant from the exits of the building, okay? Now, the 3 exits create a what? They create a triangle, don't they? Okay? And so if I want to pick a bathroom or put a bathroom equidistant from the exits, where might I put it? Okay, the center of what? Just the center of the square? If I put it at the center of the triangle, it may or may not be equidistant. I'm going to put it at the circumcenter, aren't I? Because the circumcenter is equidistant to the vertices, and the vertices of the triangle are the exits of the building, yes? Okay, so I can kind of just eyeball it, and I may not be perfect, but let's say, okay, I'm going to go here. That looks to be about the perpendicular bisector. Of course, if you were an architect, you could do a better job here, and maybe here, okay? So you would want to put your bathroom about right there, because this point is going to be equidistant to each one of the exits. Another example. In your kitchen, how many of you have an island in your kitchen? Or seen one, okay? Seen an island in the kitchen. Isn't it nice if that island is somewhat centrally located to the 3 most important things in your kitchen? What are the 3 most important things? Your fridge, stove, and your sink, right? Because your stove and your microwave are using together, right? So, and you use your water, you need to wash your hands, right? Okay, and you get stuff out of the fridge, okay? So, to be a good working kitchen, you're going to want to put that island equidistant to the sink, the fridge, and the oven, yes? So you would put that island at the circumcenter, right? And the circumcenter is created by the perpendicular bisectors of the triangle, right? Okay, alright, so there's a real life application there for you. Now we want to talk about another bisector of the triangle. This is the angle bisector. Okay, now you know what an angle bisector at least I hope you do. A line, a segment, or a ray that divides an angle into 2 congruent angles. Okay, this ray BD is the bisector of angle ABC, which means that it breaks ABC into 2 equal parts. ABD is congruent to DBC, as I have marked here. Okay. We have what's called the angle bisector theorem, just like we have the perpendicular bisector theorem. The angle bisector theorem says that if a point is on the angle, or is on the bisector of an angle, then it is equidistant from the sides of the angle. So we have an angle bisector right here, and this theorem says that any point, so I've got point B here, any point that lies on that perpendicular bisector is equidistant to the sides of the angle. Now, when you talk about the distance between a point and a line, it's always the perpendicular distance. So this point here is going to be the same distance. It's not going to be the perpendicular distance. It is going to be the same distance from both of those rays, from both of those sides. Okay? That's what the angle bisector theorem tells us. The converse of that is also true. It says if a point is in the interior of an angle and is equidistant from the sides of the angle, then it is on the bisector of the angle. So notice here, B again is in the center, and we see that it is equidistant from the sides. We know it's equidistant because it's marked and the sides are perpendicular. Okay? And this theorem says that since that point meets that requirement, if I were to put the vertex in that point, then bisector of the angle. So let's do a couple of examples here. Well, we want to find the measure of angle ABD. What's going to be the measure of angle ABD? What's the measure of angle ABD going to be? ABD is 37, right? If you wanted ABC, you would multiply it by 2. Okay? We want ABD, so it's going to be 37. Now, how do I know that that's 37? Just because it looks like it? Can't do that, can we? How do we know it's an angle bisector? Cameron? But we don't know that. AD and DC are equidistant and are perpendicular to the sides. So this point lie is equidistant to the two sides. So if you were to connect B and D together, it would create the angle bisector. Okay? That goes back to the converse of the angle bisector theorem. All right, let's look at this next one. What about CD? Does CD have a relationship with anything? Yes. Okay, what's its relationship? They're equal. Why?
Because the two angles at the bottom of the angle
are congruent, right? This BD we can see is an angle bisector, right? Because what is an angle bisector? This point is equidistant from the side. Good. Okay, so before I can find CD, I have to find x. So I'm going to set 3x plus 5 equal to 6x minus 7. And I'm going to solve. Subtract 3x from both sides. Add 7 to both sides. Divide both sides by 3. And x is 4. Okay, but I need CD, not just x. So I got to go back into my problem and do 6 times 4 minus 7, which would be 24 minus 7. So that makes CD what? 17. Good. Okay. Well, just like with the perpendicular bisectors, if I go to a triangle and I draw all 3 angle bisectors, those are going to intersect at a point. And that point, the point of concurrency, is called the incenter. So I drew an angle bisector for each one of these angles. And they intersected here at this point, and this point is called the incenter. So the incenter is created by angle bisectors. The circumcenter is created by perpendicular bisectors. Okay, yes? No. It could be at different places, but it does have a relationship, which we're going to talk about, okay? The incenter, and it will be somewhat in the center, because its relationship is that that point is equidistant to the sides of the triangle, okay? So if you draw, like here, the black lines are all 3 of my angle bisectors. This right here is my incenter, and this is equidistant to the sides of the triangle, and that distance has to be perpendicular distance, okay? Alright, so that's what the incenter tells me. It's created by the angle bisectors, and it is equidistant to the sides of the triangle. Okay? Remember, your perpendicular bisectors intersected at the circumcenter, and they were equidistant to the vertices. These are equidistant to the sides. Alright, a couple of examples here. Now, in each measure, if J is the incenter of triangle ABC, J is the incenter of triangle ABC. Alright, so I want to find JF. They give me information about JF and JE. What relationship does JF have with anything else in the triangle? Yes, Lauren.
It's equidistant with the other two.
With what other two?
DJ and JE.
Correct. Okay? Because this is the incenter, then it is equidistant to the side. So all 3 of these are equidistant to each other. And so if they give me JE and JF, so I'm going to set those equal to each other. 6x plus 2 equals 2x plus 14. I'm going to solve. 4x equals 12. Divide both sides by 4, and x is 3. I still need JF though, so I got to go and plug in, and that'd be 2 times 3 plus 14. So that'd be 6 JF 20. All right, now we got to find JAC, which is this little angle right here. Now, it tells me that E is the incenter. And what creates the incenter? What kind of bisectors? Angle bisectors. So these black lines here are all angle bisectors. So if this right here is 34, what's this? 34, which means this whole angle is what? 68, okay? This is 32, so this is 32, and so that whole angle is 64. Okay, well I still need this little guy down here. What am I going to have to do? I'm going to have to add those together and subtract 180. So 68 and 64 is 132. So I have to do 180 and subtract 132. So then you give me what? 48. So this angle here is 48, which means that little green dot there is what? That green angle is 21. So the measure of angle JAC is 24 degrees. Okay, so let's recap real quick. Perpendicular bisector goes through a segment. How? Where? Goes through the midpoint, pretty much between the part, and it is also perpendicular, which creates right angle, right? Or, yeah, 2 or 4. Yeah. Okay. Any point that lies on the perpendicular bisector is equidistant from the endpoints of the segment, right? And vice versa, if you have a point that's equidistant from the two endpoints, guys, I've not done this one, put your stuff up yet. Okay? If this is equidistant from the endpoints, what does it lie on? Perpendicular bisector. Now, what if I draw all 3 perpendicular bisectors of a triangle? Where do they intersect? Well, what's that point of concurrency called? The circumcenter. And what else do we know about the circumcenter? It is equidistant to the vertices. That's a whole lot of vocabulary in there. That's a whole lot of things you got to remember. So you're going to have to come up with a way you're trying for it to work, okay? All right. Then we talked about angle bisector. Angle bisector does what to an angle? Bisects it, which what does that mean? Not two sides, two angles. Two angles. If it's an angle bisector, it creates 2 angles that are equal. Okay? And if you have a point that lies on the angle bisector, it is no. It's equidistant to the sides, right? And it's got to be the perpendicular distance. And vice versa, if you have a segment or a point, excuse me, that is equidistant to the sides, that point lies on the angle bisector. Okay, good. And so if you drew all 3 angle bisectors of a triangle, where do they intersect? They intersect at the incenter, right? And what's the incenter's relationship in the triangle? It's equidistant to the sides. Okay? So that's an easy lesson with a bunch in there, right? So you're going to have to try to figure out how to make it all work in your brain. Okay? Go back over it again. Okay? All right, your assignment is on page 329.